Should I be wearing headphones because there's going to be...
Hello, and here we are today with Dr. David Trossman. Can you hear everything okay, David? Everything working okay for you?
There's a delay.
Yeah, there's a delay between the Twitch stream and our actual talking. So it might be better to, if you want to watch the meet just for the conversation piece and then look at the channel for the chat and see what's going on with that. So
yeah, it disappears if it's less annoying if I mute it.
Right. Yeah. Cool.
So got it.
Awesome. And today we're going to talk about oceanography. We're going to talk about climate change, displacement of peoples, and whatever else we come across on these topics. So if you just want to give a quick introduction of who you are and what you do, that'd be great.
I could use the slides, actually.
Oh, okay. I'll switch those back over.
I thought it would come up.
Yep.
Or actually, so not to give my life story. So
Okay.
I don't know if I could control the slides.
You can tell me what to do.
Okay.
Which number? 50? 10? I'll just... Is there one in particular you had a thought to...
Okay, so go to slide 9.
And what's on that slide? That's...
statue raising a fish.
Yep, got it.
Okay.
Statue raising fish, there it is.
So I'm an oceanographer by training. This is the type of artwork that I saw growing up on the left in all the museums in Chicago. And on the right is what I saw in the Seattle area. The Seattle area kind of it spoke to me with its bands. When I was growing up, I heard a lot of bands from Seattle, and I thought, if Seattle feels the way that music does, maybe I want to experience that. So I ended up going to graduate school in oceanography. There's a longer story than that. It's not as arbitrary as that, but I ended up going because I was in physics at the time, and then just I thought that it was physics was pretty well taken care of by a lot of people. So I thought that studying more of an application to physics, how it was relevant to people. The ocean's role in climate seemed like a good way to do that, and so that's what I went to graduate school in, and that's what I continue doing today. I study all sorts of things about the ocean, mostly the physics of it, how it moves, how we monitor how much heat is in it, and the stuff that gets into the ocean and how it moves around. So that's in a nutshell. But so if you could go back.
Alrighty. Got it.
If you could go back to the second slide.
The painting and the
yes,
ship in disrepair.
Yeah, the ship. So the painting. This is the kind of artwork that I saw when I went elsewhere near the ocean. I had no idea what the ocean looked like, and that was the kind of representation that I saw. And on the right is the kind of stuff you see on the Great Lakes. Just a lot of ships in disrepair. There's a whole ship graveyard in Lake Huron. There's a museum about that. And my uncle, he took me out to onto Lake Michigan in the middle of summertime, and I was impressed just how big of a temperature difference there was when you're out on the lake and versus being on land. And I decided from there henceforth that I would never go out onto the ocean because I hated it so much. So somehow I ended up an oceanographer, but I still haven't actually been out on the ocean. I just do. I program a lot. I use a lot of coding languages, Fortran, R, MATLAB, things like that. And I run models, large numerical models that people have written over decades.
And that's where that physics background kind of came in to aid in that modeling and the programming side.
Yeah, the physics was very good for that. I also majored in math, but that was just a lot of proofs. Ultimately, I think most of the skills that I have came from physics. But math taught me how to think logically. Clearly, the order of these slides. Maybe you would think that I'm not very linear in my thinking, but that's how they stumbled across it. But we could go to. Well, yeah, the first slide. Why not? So the first slide is just to show people how old I am. So that carbon dates me, the picture on the left, and later on, I taught a class and I told them to draw what an oceanographer looks like, and that caption on the bottom, the octopus-looking thing, that's what they drew.
I see the resemblance.
On the right,
that's
sorry, go ahead.
I see the resemblance.
Yeah. Before I grew a beard, yeah. And on the right is what I grew up reading. when you're 2 or 3 years old, you might see some of these picture books, and this one was about the ocean. And this one was, I didn't know what to think of this, though. I reinterpreted it decades later, and what they're saying is, please help preserve the ocean so we can reap its resources.
Okay. That's sustainability, right?
I guess. Yeah. So that's where I'm coming from here. I came from a place where I never saw the ocean and ended up staying, and now I'm in another place that's not really on the ocean, but kind of connected by a river.
Well, everything's connected to the ocean, right? That's
ultimately, yeah.
Yeah. Yeah. And the other thing I noticed about your slides, there's a definite connection to art, which I don't think a lot of people outside of the sciences, they think that art and science, I think, are somehow separate, whereas there is definitely some commingling of art and science, and it's always been that way. And I went on your Instagram and I've seen a whole bunch of these slides, of course, and that art piece is really there. So does like art really speak to you in a specific way that you want to talk about?
Yeah, that's mostly what these slides were about. Glad you are bringing it up. The third slide, so the one that you're on, that one is it's at the zoo in DC. I saw this. There was this exhibit. All of those pieces are made out of plastic bits that they recovered from the ocean, which I thought was incredible. I mean, I at the time I never really pictured how much plastic there was in the ocean, but not long after that, a bunch of studies came out just showing how much is there or likely there, because people were trying to figure out where's all this plastic that was supposed to be on land, and then people began discovering the great garbage patch in the Pacific Ocean, and it's at the centers of all the what are called gyres. So it's like a toilet bowl, in that it just swirls around. That's how you can picture it mentally. But there's a good reason for that structure. It has to do with the winds and the fact that the Earth is rotating, and because of those factors, plastic bits tend to accumulate at the centers of them. There's one in every hemisphere and ocean basin. So there's one in the North Pacific, North Atlantic, etc. And people still can't balance this budget of how much is missing from land, and then how much they actually see in the ocean. And so people are thinking, oh, well, it actually might have fallen down to the bottom of the ocean, got buried in sediment. And so people are finding some evidence that it's there. And people have seen a plastic bag at the bottom of the Marianas Trench. And
they're everywhere else. Might as well be there.
Sorry?
Their plastic bags are everywhere else. They might as well be there as well, I guess. Unfortunately.
Yeah, it's I found it kind of profound that we could touch every single corner of the Earth. So I think 3 people have now been down to that deepest part of the ocean, but plastic bags were there before many of them.
Now,
there have been more people on the moon than there have been to that part of the ocean, yet we've placed plastic bags there.
Yeah, those plastic bags don't get up to the moon for some reason.
Yeah, I mean, well, we've left flags, we've left these reflecting devices that have given us information about how far away the moon is drifting away from the Earth per year. It's about a fingernail's length per year. And so that's an incredibly precise measurement for just leaving a reflector device on the moon and aiming it from Earth and taking a measurement. But anyway.
And one of the questions I have that we're talking about plastic is that, a topic kids learn about a lot. Even in my class, we'll talk about the Pacific garbage patch, because if we do independent research on plastics, which I do next month, a lot of kids will choose to do research on it. And there's this misconception that it's this big chunk, like there's so much plastic you could walk on it. But that's really not the case, right? It's just more concentrated. I think there's a misconception a lot of people have that it's this garbage patch. It's just like all this plastic in one spot, but it's really more dispersed. I kind of see it as more of like an asteroid, belt, where in the movies you see all the asteroids really close together, where in reality they're thousands upon thousands of kilometers apart. So could you kind of get into that a little bit?
Yeah, that's a good analogy. So if you see an article about it online, you'll probably see a picture of just a whole bunch of junk clumped together. Mm-hmm. But rarely do you see them. Actually, most of the plastic in the ocean are these microplastics. So, you wouldn't even spot them with your eye. But there's so much of it that if you clumped it all together, the mass is just incredible. I don't know the numbers off the top of my head, but the particles, it depends on what they're made of and how big they are, whether they're floating towards the surface or close to the surface versus closer to the seafloor. And people thought that most of the plastic would be buoyant enough that it would be close to the surface. And that's why it's surprising people that there must be a lot near the seafloor, and they're finding evidence of it.
Okay. That verifies what I had thought and I had already read. So that's why I like getting to the source and talking about that.
Another much new, but this isn't something that I researched myself, but I can. What's this guy's name? I could come up with it really quickly. Let's see. It's Van Sabilo. He's in the Netherlands at Utrecht, and if you want to, if you want to know the latest research about this guy Eric Van Sabilo is the place to go to, and then if you want to know the latest about the measurements of plastic, people trying to see where it's going and doing inventories, Carol Lavender Law is an excellent person to go to as well.
Because I will say it is something that's in the public, psyche. I like my students are always asking about plastics. It's in the media a lot. I mean, there's the huge thing about plastic straws about a year ago, where I know in my area there were all the restaurants were trying to get rid of straws, and and then there's the backlash of how much is that benefit. And so it is something that people are cognizant of, even kids on down to elementary age are thinking about these topics. And so I think that's good for the world that the younger generation is kind of getting involved and thinking about these things and doing research into it. And I think there's a lot of more research, of course, that we need to do, a lot more questions than answers. And then there's that famous, event where that container ship of rubber duckies crashed, right? And those rubber duckies went all over the ocean and initially tracked where different things went. That was plastic as well.
So those rubber duckies were buoyant enough that they were right at the surface, and so they were tracking large-scale ocean circulation at the surface. They weren't tracking anything that happened beneath. They weren't tracking the complex overturning structure of the ocean. So you asked about, I mentioned the overturning. So how about we go there?
Okay.
Go to slide, that's 12.
They're not numbered, so I have to kind of guess it.
Yeah. Oh, okay. Sorry. It's the Tetris pieces.
The Tetris pieces. Okay.
Keep going. Yeah, we'll read those comics. They're good. You missed it.
Oh, geez.
Go back up.
The sea surface one.
The AAAIW. Yep. Yeah, that one. So the overturning circuit. So the ocean has this complex structure where it has currents, it has water masses mixing with each other, and so some of them sink, and then they somehow get back up. That's another interesting question. People are finally understanding more deeply how that's happening, but classically, oceanographers found that there are different regions, masses, huge areas of and volumes of water that have similar properties, or they have a single characteristic that distinguishes them from other huge volumes of water across the ocean. And so, as I was trying to communicate this point to people, I thought, well, they fit together like Tetris pieces, because there isn't there aren't very many regions of the ocean that are just unclassified by this traditional view, and so I put together this this Tetris diagram where I'm trying to show the structure of how the ocean moves in general. So it goes around. If you're looking at it from Antarctica on the left to the Arctic on the right, so this zonal view, then these dashed circles on the top right, that's supposed to show that there's water that's sinking there, and the water that forms after it sinks. So the winds are stirring up the ocean, and there are certain conditions under which the winds can penetrate down to about 1,000 meters depth in some places near Greenland. And people have put a bunch of arrays of measuring instruments out there and have been figuring out where that occurs. And it's near Greenland. It's mostly occurring to the southeast of Greenland, but there's some to the southwest as well. And all the water that forms after the winds during the winter time can penetrate down to about 1,000 meters depth, mixing up the water all the way down to that depth. What's left after that season passes, when that mixed layer, so to speak, it gets shallower, is a water mass. So it has well-formed properties below that layer of water that's mixed by the wind. So it has these set properties then until the next time that it gets in contact with the atmosphere through that layer. So that layer, that mixed layer, is the conduit between how the interior ocean communicates with the atmosphere. And so that's how a lot of heat gets down into the ocean. That's how a lot of carbon dioxide gets into the ocean. About 1/4 of the carbon dioxide that we emit gets into the ocean. Over 90% of the heat that we've been accumulating on Earth due to that carbon dioxide has gotten into the ocean. The ocean's a buffer in that way. We would be a lot warmer if it wasn't for the ocean in many ways. But so this water mass that forms when water gets mixed down that deep, and then the water doesn't get mixed down that deep after that. The water that remains is the NADW. It's this North Atlantic deep water. So that's that Tetris piece. And then you have others in the southern hemisphere. You have kind of a similar process, but it's because salt is forming from ice. Salt is being rejected from ice that's forming near Antarctica. And so that salt that gets rejected, it goes down into the ocean, and it helps form this very heavy or dense water mass called Antarctic bottom water, that AABW, the orange piece. And then there's also this relatively fresh, so not so salty piece that remains at the surface, and that's more complicated. Antarctic intermediate water, and I just filled in the gaps there with that. There are other water masses too, but I just tried to simplify it here. So the bottom circle with the Antarctic bottom water, I'm just saying that eventually that gets eroded, and water down there, that goes all the way down to the bottom of the ocean, and it fills the ocean seafloor almost. It goes far north. It takes a while, but it gets to the North Atlantic, gets to the North Pacific, and eventually it gets mixed with other water masses, and that water can come back up under certain conditions, having to do with the slopes of the topography, actually.
So this is the currents that are going, these huge currents that go through the oceans, and then they, the warmer water rises, right, and then it cycles again, and that cooler water sinks, and so we have these huge currents. Am I correct? And since you're studying this, and this is where climate change could disrupt these currents.
So that's you're talking about convection.
Yeah.
So the convection cells, say you picture a room where so the room isn't very big, but you have a heater near the floor, and so the air rises near the heater, and then at a different part of the room it'll cool and start falling, and you form this cell. And so it looks like it's a similar phenomenon here with this cell forming in the ocean. But
this one's based on density. But this is based more on the salinity density differences.
It's
and
one
wind
dominates over the other depending upon the region. So it's
okay.
very complicated. Salinity dominates how dense a water mass is near the poles at the high latitudes, Antarctica, Arctic, whereas temperature tends to dominate elsewhere. And you also have this interplay of the density contrasts across space that does drive the currents in the ocean, in the interior generally. But then closer to the surface, you have the winds mostly driving the ocean. And then you also have this complicating factor of mixing. So the right here is an art piece. So all these art pieces are bad, I know. You don't have to point it out. I made bad art, but
this wasn't you. This was a small child.
It was someone who was learning how to do each one of these media as he was going.
Yep.
But
it makes sense though. I mean, I'm looking at it, and it's like, oh, okay, right.
So on this one, I'm trying to get across how water mixes. So there are many ways that it can mix, and it complicates how the water, that overturning circulation occurs, because You have when you have one water mass coming across another, they tend to be of the same density. So water follows constant density surfaces generally in the ocean, but you can have mixing across density surfaces if you're inserting energy into the ocean in some way.
Right.
One of those ways is the wind. The wind can generate waves. Those waves can break, and those breaking waves can cross those density surfaces. Another way is the tides. So the tides are moving, sloshing water back and forth across the seafloor, and if there's any lack of symmetry in how it passes over topography, you can get some breaking waves. And so what I was trying to draw here is that so you can feed a water mass from above with salt, like where there's Antarctic bottom water forming, and then from below you might have these hydrothermal vents. That's very hypothetical. They aren't going to be close to each other very often, but that's the conceptual diagram I'm drawing here. So they can be heated from below or get denser from above, just like you were thinking with that convection cell in the room.
Right. And then you have consider you have in Greenland and Antarctica, if you have a lot of melting fresh water, right, coming into the system, then it stratifies and mixes even more.
So then there's an even more complicated story. I mean, I could go on a lot of tangents.
You have a really complicated field of research.
Well, I mean, this is pretty well understood. It's the geographic patterns that are happening at the moment with how the melt from the land ice in Greenland or glaciers in North America and other places get into the ocean, and then the pathways that fresh water follows. All those details are not very well known, but they're approximately known. We know that the end result is that so you get this fresh layer on the ocean. Yeah, you're right. You get stronger stratification. So the wind can't actually punch through the ocean to 1,000 meters depth like it could. And so this was kind of the premise of The Day After Tomorrow, where you have these extreme cold events suddenly in the ocean. I mean, the movie took it to a ridiculous Hollywood extreme, but
of course,
the basic picture is that you're going to slow this overturning cell of the ocean because you're making less of that deep water, the North Atlantic deep water, and so you're weakening the overturning cell. It's not being driven as quickly, but there will always be the winds, so it's not going to shut off altogether. It's just going to weaken, and that. So, but to go back to the bad piece of art, there are two types of mixing that can happen. You can have water. So, like I was saying, the water can come across each other on constant density surfaces, but they can have different temperatures and salinity. So, when you have different temperatures and salinity coming across each other, but the same density, water will mix together. And you can have this. It's called cabling effect. So they have different pressure when they're coming across each other, and also a different temperature, and so you get this cabling. And also it's called thermal voricity. And so you have, but the important point about that is that when they have different temperatures and salinities, they will mix together and always get more dense. So it's because of how density is related to temperature and salinity in the ocean. Water that's the same density but different temperature and salinity will always get more dense, or at least stay the same density. And so then you get water sinking, and that's how, I mean, that's one mechanism for how some of these water masses can form, but it isn't the dominant one. But you then ask yourself, how does water get back up if it's always getting more dense when mixing with different water masses? And so that
yeah, I guess it makes sense. I'm trying to think about it, because to me it's like it's going to get more dense. But I guess if you have fresh water, it can only get more dense, and salt water is just salt water. It's not going to get more dense. So water will, in that case, always become more dense or stay the same density. And then, if it's cooler, it's going to sink as well. So unless like you said, unless there's a volcano underneath making it a lot less dense, then you're not going to have that necessarily. It's always going to be more dense and sinking. Right?
Right. So I mean, you would expect that the ocean just keeps filling up with denser and denser water over time, but it doesn't.
Mm-hmm.
So that was an interesting question to me when I was in graduate school. But people have addressed it. They've been doing more idealized studies where they just have this model bathtub, and they're seeing whether the fact that the ocean kind of resembles this bathtub if you look at it from south to north, whether those sloped sides have anything to do with it, and indeed it does. You don't have to rely solely on those hydrothermal vents making the water less dense. It's the shape of the seafloor also matters. And there are a lot of complicated features near the seafloor, and so there are a lot of places where water can actually come back up.
Now, does the pressure of the water matter at all as well? I mean, because I know that can affect temperature. So what does water pressure have anything to do with these currents?
Yeah, so like I was saying with cabling and thermobaricity, so one of those means that different temperature and salinity mix together and create a more dense water mass. The other is that water of different pressure and temperature come across each other and create a more dense water mass. And so the pressure actually does matter. Pressure also matters in these contrasts in pressure in orientation with the contrast in the density of the water. This is getting very fluid dynamic-y, but if you take this, if you take the sine of the angle between them and multiply them all together, then you get essentially the effect that's it's called baroclinic instability. So there are these unstable columns of water. They kind of they change the slope of these constant density surfaces. So you know how they're shaped like the bathtub, like I was just saying.
Yeah.
And they will slope. The slope at the high latitudes will get less slopey.
Yeah, it's getting a little more complex than.
Yeah, it gets pretty complicated from there on. But the water re-stratifies
right.
essentially when that occurs.
Right.
So you might have had a relatively homogeneous water mass there, but if a baroclinically unstable event occurs, then you might have one water mass separated from the other because it's more stratified. So.
Okay, that was a brainful right there.
Yeah, that was intense.
But I like it. It's interesting because it's a lot of it is, I teach 8th grade science, and we talk about pressure, density, and convection, right? And essentially this is all of that put together, and then some math thrown at it, as well as modeling, which is what you do. So I mean, at a fundamental level, it's the stuff you're learning in 8th grade, but you're just going up to that much higher research level, but it's the same fundamental principles though that kind of dictate what happens.
Yeah.
So where are we going to go now?
Yeah,
I love you.
Well,
is this all original artwork? I'm fascinated.
The ocean. So where does that energy go? Go one slide up.
One slide up. Okay. This roller coaster?
No, the opposite direction.
One slide up, meaning down.
Yeah,
okay.
The train wreck. Hopefully, it's not a metaphor for how I'm explaining things, but the train wreck is showing. So one process that I've put into a model. It's a wave that's generated as flow goes over a topographic feature at the bottom of the ocean. That's all that's trying to say. But on the right, there's a tombstone.
Okay.
Are we there?
Yep, got it. You got the tombstone.
Okay. So the tombstone, I wrote a terrible poem, and that's trying to talk about this concept of so mechanical energy. So how much energy you're putting into the ocean to put it in motion, and there was a pretty large uncertainty about how much energy that was at one point, but the winds put in about a terawatt, a tera being a lot. It's 10 to the 12th watts, and watts is joules per second. Joules are the energy in it, and then you get about 2 or so terawatts of energy from the tides. So the tides are putting in a lot of energy as well, and the net.
Now, is that globally though? That's like the entire Earth? That's the amount in there, or is it ocean. Like per something? It's the entire globe.
Yeah. So
okay.
That's you could put this in terms of per meter squared if you like, if you want to know the density of that.
I'm just trying to get my idea around that terawatts,
So this is just how much energy is going in globally and then ultimately being dissipated. So this energy doesn't just accumulate, because you might think that the ocean could be getting warmer as a result of just all this dissipation and resulting heat, but no. The heat is coming from the atmosphere. You can see that very clearly from how much warmer the near surface of the ocean is compared to the deeper ocean. And the deeper ocean is actually where most of the dissipation is occurring. So the dissipation occurs near the seafloor generally. And then there are some breaking waves as you get higher in the water column, and then closer to the surface, there's a bunch, but it's generally close to the seafloor.
So some amount of temperature, though, is due to the tides. Just that energy that's put into it.
There is a small amount.
Okay.
Yeah.
I never thought of that. That fascinates me. I never even.
So that's actually the reason why the moon is drifting away from the Earth.
Right. Huh. Because it's dissipating that energy, so it's.
Yeah. The energy is not conserved between the two bodies. It's actually dissipating,
Hmm.
little by little.
Right.
And then, so the way that it gets dissipated are these mechanisms, like on the left, these waves being generated and then breaking. So you're inserting that energy to be able to move the ocean, and then it generates waves, and then those waves break, and that's losing the energy.
Right. And is that energy is released as heat mainly?
So
lost in that way?
There's some heat, but
sound energy
mostly just gets converted into other types of energy, like potential energy.
Mm-hmm.
So it does work in order to bring up water that's more dense to water that's less dense. And so it's the ocean is this huge reservoir of potential energy that way. But how much of that can you actually tap in terms of energy?
Right.
So there's this concept of available potential energy, and that's how some of these little features of the ocean, when you have those baroclinically unstable events, these little features that are anomalies occur in the ocean. And yeah, so I don't think I should go into more detail.
Okay. I just think it's interesting, again, where it's like I always relate it back to the basics of 8th grade, where we talk about kinetic and potential energy, and it's another case of this fundamental concept is, built upon to do this, this thinking that we're doing as far as an oceanography and energy conservation. So
yeah, there's no way that an oceanographer could fully understand what's going on without that basis, the physics backgrounds, the potential energy, kinetic energy, that understanding of what that means. So awesome. we can go on to the knitted elephant seal.
I wanted you to talk about your. Is this more of your artwork? Is that
okay? Yeah. I mean, all of this is my artwork.
Nice, so, very good.
Or I mean, I should say that it's not mine because it's so bad. But yeah, this is just I loved the concept of this. So oceanographers have a difficult time just observing the entire ocean.
Mm-hmm. I
mean, how would you design a network that's cost effective? I mean, or a reasonable has a reasonable budget that the government was actually fund, or all governments in the entire world actually, and be able to cover enough of the ocean to know something about it. Because classically, people go out on ships, which I just talked about that I will never want to do, and because I will barf, and I will barf for however long that cruise happens, and so I will probably die from lack of sleep and dehydration and other things. But so one ingenious way that people have come up with to cover the ocean, to observe it, is to strap instruments to elephant seals. So they oceanographers. So like I was saying, they go out on ships. They put measuring devices down into the ocean. They take a profile or two. Several usually, and then they might capture some water samples in order to see what kind of tracers are in the water, like CFCs that we emit from our air conditioning devices are used to before the Montreal Protocol, and then and now other types. They'll measure how much carbon's in there. But they'll measure the temperature, salinity, pressure of the water, and they'll have one profile of the entire ocean. So then they have to sample the ocean many more times in many other places, and usually they just go along this just a transect, so just a straight line or
Right.
approximately straight line of the ocean from one continent to another. That is many weeks of work, and you just have one line of the ocean. Basically, we send people out to do those transects. We repeat them every so often, maybe 5 to 10 years or something, depending upon the transect. And then what you have after taking all those transects together is what looks like basically our highway system. So imagine you're just driving across the country, across all the highways in the country. Then you peer off the side of the highway, and that's all you can see. So how well do you know the U.S. just from driving on the highway? I don't think anyone would argue that you know it all that well. No one wants to live near the highway. That's one reason, but also even if people did, would it be representative of the entire country? Probably not. And people have done interesting sampling experiments where they found that, the way we take these transects with ships isn't very representative, especially in the deep ocean.
So you've got to strap fancy electronic hats to elephant seals.
So these ships, they can't go in place without an icebreaker. They can't go in places where there's sea ice. And so icebreakers, there are very few of them, even fewer than there are ships. The U.S. has a dwindling number of them, and so we don't collect that much data from those ships, and so therefore underneath sea ice. So we have to come up with creative ways to collect data below sea ice. And this is one of them. These elephant seals dive to over 1,000 meters depth, and they go directly beneath the ice. And then once they come back up, they relay the data. They know to press a button. No, they don't have to press a button. And the data get transmitted to a satellite, and then that satellite relays the data back to us on land.
Now your research actually uses this data from these elephant seals?
I use it.
Oh, okay.
So
That's pretty cool.
Just compared satellite measurements with the data that these seals collected. Satellites only see the surface, so I just used the measurements they took very close to the surface. But people use it for other things as well. You can put it into a model and try to nudge the model to be closer to what is observed, because our ocean might not have the initial conditions of our models might not be perfect. So when we're trying to forecast into the future, we have to correct for those initial condition errors. And so people have come up with fancy statistical ways to try to nudge the model to the state of the ocean as observed by these elephant seals, as well as ships, as well as these Argo floats. These Argo floats, they are these automated devices. There are 3,000 of them all over the ocean. They cover the ocean except where there's ice. They go from the surface down to about 2,000 meters depth, and they come back up to the surface and they relay data to satellites, and those satellites relay it back to us on land. So satellites are really amazing in being able to observe not only the surface but also the ocean interior because of elephant seals, Argo floats. So we use all those data in order to nudge the model to be closer to reality, up to the present.
How accessible is the data? Is it available to the public? It's on a GitHub or something?
Yeah. So most of the data are publicly available. So there are certain satellite products that people come out
Mm-hmm.
with that are eventually publicly available. The satellite data um, that are used to nudge the models to get better initial conditions for forecasts, those tend to be um, lower level, so they aren't as processed. Uh, so we have the swath of the satellite coming across this certain location, and without interpolating or filling in the gaps in any way. Um, and so those data aren't always publicly available, but
Right.
the product that fills in the gaps and that you just want a broad view of the ocean, what the sea surface looks like, you can get those. Those are easily accessed, and NOAA has uh, uh,
Yeah.
an entire branch devoted to making a lot of these data available. Um, Everything ranging from elephant seals to drifter measurements of what the currents are doing near the surface, to current meters that are sparse all over the ocean, but they sample the currents very frequently and go down to the seafloor sometimes. Uh, and you also have the Argo floats. Those are always publicly available. You have uh, you have those shrimp transects of the
Mm-hmm.
measurements of temperature, salinity, the tracers. Those are all publicly available. So if anyone's skeptical of the fact that the ocean's been warming, you could just download the data and see for yourself.
It's happening.
I,
Yeah, exactly. You don't believe someone else's research, you can do your own. And if science works the way it's supposed to, you'll get the same thing.
I don't know why that's not brought up more often when someone is skeptical of the science. Yeah, I mean, we're making this publicly available, I think, in part because of people who are skeptical, and we're trying to make it available so that they can see for themselves if they don't trust the scientists. Yeah.
Mm-hmm.
I mean, you can't do that with vaccine trials, unfortunately.
No, well, things like NOAA are, funded a lot with taxpayer dollars, so they are.
Yeah.
I did buy them in a way. So
everyone's invested. Yeah.
Yep. Oh yeah. And do you know or have you been involved in any citizen science projects using the data or observations? So I'm pretty sure there are probably a few.
So I wish I was more involved in citizen science. So when you submit a proposal to an organization like the National Science Foundation, NSF, you're supposed to have this broader impacts statement. Mm-hmm. And so in there you can have citizen science. So in addition to the research that you want to do, you have to make an entire interface for the public to use if you want to do that kind of work. And so either you need to come up with, either you have to program that interface yourself or find the funding. So either in that grant or elsewhere, in order to fund someone who would create that interface that the public would then use. And so it's hard to do those, unfortunately. I wish it was easier.
Right.
So people generally do things like summer schools. One of my postdoc advisors, he does a regular summer school. I guess not this year, but in Ghana. And I think they're more generally doing it in other West African countries now. Mm-hmm. I think they did one in Nigeria. And I mean, they have a vested interest in the ocean too. They have oceanographers. They have agencies trying to forecast the ocean. They're interested in the Gulf of Guinea, I believe. And one of the fellow postdocs in his lab ended up a professor there. There's there are other outreach efforts that are just like workshops, trying to get more students involved in the science, and so it isn't really outreach to the public per se, but getting so we're hopefully welcoming to more people, and as they realize just how important much of the work still is to do, but also in the future. I was just thinking today that there's a heyday for every field. When is the right time to get into it, and how do you know? But then there's also, regardless of what time you go in, there's the possibility of doing something so interdisciplinary that it's never been done before, and it can be very useful and pretty profound in impact on society. For example, there are now climate economists. I mean, people might think of economics as this non-exact science, but I think that's the kind of language that a skeptic uses about climate science as well. But climate science is actually very exact. I mean, oceanographers used to be okay with orders of magnitude. If they got an order of magnitude correct, within an order of magnitude, a factor of 10, then they might have been happy, but not anymore. People have been trying to narrow the uncertainty of how much the world was going to warm, and involved in that is knowing about the ocean. I mean, if you don't know how much heat is going into the ocean, you can't possibly know the rate at which the world is warming.
Yeah.
But climate economists are now trying to quantify just how much. So because the language that a lot of politicians speak is what dollar sign is my community that I'm representing going to experience and have to pay, and how many people am I going to lose? Demographers and economists are very important to bring in.
And once the insurance agencies get involved, then it's serious.
So yeah, and I don't know of enough climate economists. I mean, there's been some great work done by people like William Nordhaus. I mean, he got a Nobel Prize for it. But I mean, there are plenty of other people as well. And
so let's segue into So we're talking about now, human impacts of climate change and how, the study of the oceans, directly impacts, populations. And I know you wanted to talk a little bit, about that, and I have some things, I can add to that as well. But this is, like you're saying, this is where all of a sudden oceanographers have become very valuable, because we realize not only will it affect homes, it'll affect economies, it'll affect pretty much your way of life. And I think it goes beyond just coastal peoples, right? Because if people get displaced, where are they going to go? Everywhere else. So it's not, I think it used to, even 5 years ago, it was mainly, climate change, it'll just affect, the coasts. But I think there's a growing realization that it's going to be a lot more than that.
Yeah, so if you want to go to the next slide, I could talk about this extremely bad piece of art, and just kind of the purpose of the work that I'm doing these days. So the purpose is ultimately to improve those initial conditions of forecast in order to improve the forecast. And so what forecasts matter in terms of I'm taking satellite measurements of how salty the ocean surface is, and that matters a lot to being able to initialize those models for forecasts for hurricane modeling. So how accurate are our hurricane models? That's on the next slide, but I'm just trying to say on the left here that hurricanes feed off of the heat in the ocean, and then on the right, just that rain events can leave fresh layers, but then the ocean is kind of the salt shaker that it can then make that vanish without a trace because
Right.
it's such a vast reservoir of salt. But yeah, now let's go to the next slide. And I think this is the one with a lot of yeah, there's a lot of data here.
So we have a question in the chat from Volcano Doc. How does the saltiness of the ocean affect hurricane strength?
Yeah, so it's mostly the heat that's feeding the hurricanes, but the saltiness that indirectly affects the hurricanes because that affects the transport of water to particular places near the surface, and then what the hurricane sees and what the transport, the exchange between the ocean and atmosphere, that gets set by the various transports of properties of the ocean towards the surface. So it's kind of an indirect effect. So the saltiness, the reason why it matters here is that it affects the initial conditions of the forecast. So if you don't have that, then you might not get the forecasted precipitation correct.
So at NOAA, this is what they would actually kind of look at to make their forecasts for hurricane seasons and for hurricane formation, is that satellite data that you use.
Yeah, exactly. So the satellite data that I use, that's getting incorporated into the models, and that sets the surface condition, and that influences the exchange of properties between the ocean and atmosphere. That then influences the hurricane strength.
Okay.
So when you have more water evaporating at the surface, and more water content going into the atmosphere, then you leave behind a saltier ocean.
Okay.
And vice versa. So you could have a fresher ocean if it rains, and so it's very important setting what that boundary, how salty of the boundary it is.
So there's actual satellites that can like tell the salinity of the surface water. That's like a thing.
Yeah. So
that's amazing.
We have satellites going around the Earth. There are two right now, SMOS and SNAP, and they passively listen basically to a certain frequency band from the surface. So radiation going back out into space, because I mean the Earth is not a perfect black body, but all bodies are emitting radiation of one sort or another. So the ocean is no exception. It's emitting some radiation out into space. You can listen to one frequency band of that signal, that radiation, on these satellites, and that's translated then into how salty the ocean is. It's pretty incredible, actually, that you can use that information to know how salty the sea surface is.
That is incredible. That's crazy.
But sorry.
That's crazy. I never thought about it.
And I mean, similarly, I mean, you can use other types of radiation in order to be able to probe how warm the surface of the ocean is. All these have different effective depths of the ocean, though. So if when you're listening passively to the ocean to tell you how salty it is, then that's about a centimeter of the surface. So you don't know anything below that. When you're using other types of measurements to know how warm the sea surface is, that's a micrometer. It's like a hair, a hair's width of the ocean surface. And so you have to account for those when you're putting that into your model, because the model does not resolve those layers. And so then it gets technical, but
this also goes back to where you were talking about the orders of magnitude or the precision that you can get now with satellites versus before. And even when we have newer satellites that are sent up, you'll be able to get even more, precise data, right? You can get more, orders of magnitude accurate, data.
Yeah. So, I mean, the salt in one location, a kilometer or even 100 kilometers away, might be very close to how salty the ocean is, where you are. I mean, if you were in the ocean, and so how salty the ocean is varies very slowly across the ocean, but it definitely has a large scale pattern to it. Like I was saying with the gyres before, the center of the North Atlantic gyre is one of the saltiest at the sea surface. That's one of the saltiest places. Whereas south of Alaska, for example, in the Gulf of Alaska, that's one of the freshest places at the surface. So there's a pretty large difference between those two, but generally, as you go far away, I mean, if you go even hundreds of kilometers away, it's just the way the quantity we use to quantify how salty the ocean is not that different. And so we have to be very precise about it. And the small differences, though, matter. Like I was saying about the wind being able to penetrate down to 1,000 meters near Greenland, very small differences in how salty the ocean surface is can influence how far down the wind can penetrate by a lot.
I mean, I just think back to I used to sail on the replica ship Half Moon on the Hudson River, and we would take salinity readings up and down, and that you'd use a refractometer to figure it out. You'd take the water and you'd stick it on the refractometer, and you'd look through it, and it would give you a measurement of the amount, the salinity of the water. And to think,
So how oceanographers usually do it, as if you stick an instrument into the water, is how conductive, electrically conductive it is.
Okay, right. Yep, I've seen that as well. Unless you're using a satellite, in which case it just beams the signal back to you, and you can figure it out that way.
I mean, there's an interesting concept going around that I'm trying to work on, about whether you can get this measure of how electrically conductive the ocean is, at least from top to bottom, because from magnetic field measurements. So the ocean signal is pretty small in the Earth's magnetic field, but those are also being measured by satellites. If you know that the contributions from other steady sources pretty well, then you can extract what the ocean signal is. And then if you know that the ocean signal, you can infer based on electromagnetism how conductive the entire ocean from bottom to top. It's not just the sea surface in the case of the magnetic fields, because of how electromagnetism works. But so there are a bunch of interesting things still to be done with trying to figure out what pieces of information can tell you what in the ocean. But it's a perennial challenge to just be able to observe all of the ocean. With hurricanes, at least, I mean, it's pretty obvious when there's a hurricane. I mean, especially if there's landfall.
Yeah, there's evidence for that.
People it affects.
Yeah.
So this is a time series that I'm showing here of numbers of hurricanes.
Yeah.
As a function of time on the top left. And so someone in 2008 came up with this model that he thought would be able to predict how the number of hurricanes into the future. And so far, it's been a surprisingly good fit to that model. And that's extremely unfortunate because people thought that the rise in temperature, at least at the sea surface of the ocean, is so hurricanes need at least something like 26.5 degrees Celsius at the surface in order to have the conditions right for a hurricane. But there were other atmospheric conditions that would basically cancel out the fact that water would be warmer than 26.5 degrees Celsius more of the time. That's at least what a lot of climate models are telling us, that hurricanes would be more intense but less frequent. So the bottom left is showing what we've measured for temperature all over the world, the global average temperature. And
it's going up. What do you think?
It's going up. And it's going up very closely related to the number of hurricanes on the top left. And that's, like I was saying, that's kind of disconcerting. Hopefully that doesn't continue, because otherwise we might have, we don't know whether that's going to mean more landfall for the hurricanes.
Right.
But I mean, chances are it would be more landfall.
It makes sense. If you have more hurricanes, more of them will hit land. It would just kind of make sense.
If they're just randomly distributed, but I mean, then you can argue it's not going to be random, although and on the top right, it shows how well we've been doing over time with modeling the position of the hurricane.
Notice that it's getting better and better, right?
Yeah,
because your error is getting less and less.
To the right, this is the error, so you want it to be 0, and it's showing with the different colored lines how many days out or hours out you're making the prediction. And so we're getting better at that, and that's because partly because our data coverage is getting better, and so we're but partly because our models are getting better, and the confluence of those two is creating those initial conditions for the forecast. And so if you have an accurate initial condition to start your model from, that's one factor, and then you have to have an accurate model that's actually doing the forecast.
Right. Or you can just take a Sharpie and write over the map and say where it's going to go. Sometimes that works too.
Yeah, exactly. It worked very well for the present. And I believe one of the people at NOAA. But bottom right is showing that the intensity of hurricanes is also increasing. So that's also disconcerting. Or becoming more frequent, that we have more intense hurricanes.
Right, and we have the wind speed that goes with it. Yep. Well, things aren't looking good. I don't know, David. It's kind of a bummer now. You're kind of bumming me out. We got.
so we'll get into solutions. We'll talk about solutions in a bit. So you wanted to talk about why people are going to move.
Right.
So this is one of the reasons why people are going to move. But like you say, it's not just the people who might move. And by the way, the factor that hurricane experts love to talk about that actually will impact people is flooding. It's not the wind itself. So
Right.
the hurricane might get more intense, but as long as the precipitation is about the same, then the damage might be about the same, because the wind doesn't make a very large percent of what causes the damage from a hurricane. Because hurricane-prone locations like Miami, they have codes, structural codes, so that they can withstand a lot of these intensities. Although in the future, if they get more intense, then like a Category 6 or whatnot.
Well, and it's like it was the rain. I mean, I was, in my area of upstate New York for Sandy and Irene, and both of those were devastating. But it, like you said, a lot of it was that flooding. So even in a fairly inland area, those two storms had a massive effect, coastally, and not just right along the coast that 30 miles or even 90 miles, but even further inland. A large storm can still make a huge impact.
Yeah, so there are two things that people who aren't on the coast should be a little more worried about. One is the fact that, yeah, it's the precipitation from the hurricane that goes onto land that does most of the damage, and so you might be in a flood-prone area, and that's so not as much precipitation might cause more damage to your area if you're more flood prone. And so there's some research finding that hurricanes are going to penetrate farther and farther inland over time. So that's also disconcerting. I don't want to go too into these depressing details, I guess, but
yeah.
But the other factor that people who aren't on the coast should worry about is that, and they should learn this lesson from the pandemic, actually, is that people near the coast are going to move to their area. And then there's, it's effectively climate gentrification. That's a term that people coined. Like there was a study about Miami-Dade County and which homes are becoming more valuable and less valuable as a result of impending sea level rise. And so the homes in higher elevation places are becoming more valuable, and people are now being priced out of those areas. Those areas historically, policies were passed to segregate people into those areas, and they weren't valued very much. But now they're more highly valued because they're not going to be underwater as quickly.
So that beachfront property is not as valuable as the higher level, drier property.
So there's a website, floodfactor.com. It was it was an effort by the First Street Foundation, a nonprofit, to quantify a risk of every property in the U.S. So you could put in any address. Like if you're looking for an apartment to rent or buy, or a house to buy or rent, you could put in the address in this website, and you could see what the risk factor of flooding is. And so I was just thinking of moving into an apartment in Baltimore, for example, and so it was really nice, and it was incredibly cheap. And I thought it was a little suspicious that they photoshopped the photos or something, and that really it wasn't in as good of a condition as it looks like. But I looked up the address on Flood Factor, and it was a 10 out of 10 risk. This place is going to be underwater, and
wow.
I mean, there's no mention of that in the ad. The real estate agent didn't know. The real estate agent had never heard of Flood Factor.
Well, that kind of tells me that it was flooded at one point in the past. more than likely to be a 10 out of 10. And I think it's also
yeah, that's true. And
good luck getting insurance.
We also looked at a property in where was it? Yeah, Silver Spring, Maryland, and it was a 6 out of a 10 because it was right by a creek. But the real estate agent, he said this place has never been flooded. So why is it a 6 out of 10? It's because, and sure enough, they quantify the risk as a function of year, and it was essentially zero risk at the present. But in a few years, there was a 4% risk. In 10 years, there was a 30% risk. By 2050, it was something like a 90% risk of being flooded. So if you were going to buy that property, the resale value was going to be pretty low if you're
unless you did like a 15-year mortgage and you could sell it.
Yeah,
or something.
I mean, there will probably be programs by that point that will be buybacks to the government. But I don't know who's going to qualify, what conditions they're going to make, or what kind of misinformation is going to be around then. So.
Oh yeah. I know even in our area with the flooding with the Hudson River and everything, there is, the problem with getting insurance. Sometimes insurance companies won't even insure you. Or if you get the insurance, it's so, exorbitant, it's like more than your mortgage, basically, to try to get the insurance. Like you said, that,
so I mean,
the economics.
Both issues are going to be important to think about if you're going to get a property you can afford but will be flooded. So yeah, I mean, that's one of the real world implications of this work. I mean, if you're going to live anywhere, you should care about that.
Oh yeah. Yep, definitely. And this is going over globally, right? I mean, there's hurricanes and typhoons and storms and monsoons and everything else globally, which will affect the amount of either precipitation or I believe it's the opposite, where some places will become more arid, which has its own problems as well. But that has to do with the ocean as well. I'm sure everything has to do with the ocean and the global patterns that it causes.
I mean, so when I was in graduate school, there was a program on climate change that was part of the reason. That was one of the better reasons I chose to go to that graduate school. So there were students in Earth and planetary science. There were students in atmospheric sciences. There were students in oceanography, and not only oceanography, but either physical or chemical or biological, and oceanography. And the students in atmospheric sciences, a lot of them were just told, because there were professors there that they were trained in this old school of thought that the ocean was boring, or that oceanographers are people who couldn't get into atmospheric sciences programs, or just were inculcated with this propaganda that they shouldn't think about the ocean very much. Just pay attention to the atmosphere. And that quickly became an outdated mode of thinking throughout my time in graduate school, especially after I graduated. I mean, I don't think there's a single person there anymore that can exclusively study the atmosphere without considering any type of ocean being present, or the land-ocean contrast, or even atmospheric chemistry, all of which are different components of models.
I mean, didn't they learn the water cycle in like, second grade? They know, right? I mean, come on now. It's all connected.
Well, so what they did was they thought that an ocean was there, but that it was just effectively a swamp. That whatever happened, it didn't matter what happened in the ocean. That it has absolutely no physics to it, other than that it has a heat capacity, and that heat goes into it.
So it just kind of sat there. It wasn't dynamic. It was kind of static.
Yeah, it was pretty static. That you have this sea surface so they thought that the sea surface temperature was important, but nothing else was. And that's pretty untrue. I mean, you constantly have physics influencing the surface and the ocean. I mean, that's ultimately the exchange of properties between the ocean and atmosphere. That's ultimately what these atmospheric scientists were concerned about. But you can't possibly get that right or be predictive about it without those physics in the ocean interior. But still, people thought that they learned lessons by assuming that the ocean was either a swamp versus, okay, maybe it has one layer to it that is active, that mixed layer that I referred to earlier, that's right, mixed up by the winds. And so, I mean, that's what James Hansen, who is the chief scientist at NASA for a while, that's what he did the year I was born. That he showed that if you put in this mixed layer and that have that kind of ocean, it dramatically influences what climate you can simulate, and actually you get a pretty accurate climate once you do that. But it's not accurate enough. But we knew even back the year I was born that that climate change was going to have some deleterious effects. So,
yeah.
But yeah, I just think back on my time in graduate school, and I remember a lot of dismissive people. There was one person who he studies atmospheric chemistry, and so some aerosols actually come from the ocean that stay in the atmosphere for a while. I mean, there are short-lived ones and longer-lived ones, but he just told me flat out, no, the ocean is boring. Why would I take a class in oceanography? And then some other students asked me about, so what do we do as oceanographers? And I tried talking about the ocean mixing people, some large-scale ocean circulation people, ocean's role in climate people, and people who are observed by satellites, people who model. And then, so I think he lost interest after the first few words. When someone else sat down while I was talking about that, he said, oh, David was just explaining what oceanographers do. So go, David, repeat what you just said. And no, it was clearly in a tone that he was disinterested, and all of the others were as well, because they were just laughing.
That's weird, considering the ocean, covers most of the Earth's surface. You would think people would study it and research it and advocate for its, for that kind of research. But what do you know?
I don't know. People have these funny ideas.
Yeah, they do.
or just finds their work to be so important they are self-righteous about it, or They dismiss other things and just get tunnel vision about it. And I mean, I really. So I brought up the climate economists and demographers because I really appreciate that work, that they're going outside of their traditional disciplines and learning about others and finding applications in them. I mean, that's some of the most useful work that can be done.
And it's one of the things I try to, in my own class, when I talk to students as well as on this channel, when I talk to different people in science, is that there is so much that you can do in science. I mean, even within oceanography itself, as you said, there's so many different subfields that you can get into that might interest you. You know, I think a lot of students, and I think the general public, kind of think that science is one concept they have in their head of what a scientist does, when they don't really see the full spectrum of what you can do with, not maybe if you're not even in a research lab, but you're working within science as far as even politics, you know, as well, which is, you know, big. But there's so many places where you can go with a background in science, and that's what I try to tell my students, because like you said, you know, there's so much to it there that interests you, and don't have tunnel vision about one thing.
Yeah, I mean, when I mean, throughout also one thing that I think most graduate students go through is wondering whether they're going to continue being a researcher a lot of the time, whether they just want to teach or be a researcher or be a professor and do both, or but also there are these other paths, and they're not very well communicated and not so actively encouraged by a lot of professors, because they didn't follow that route. They don't have a lot of experience with it a lot of the time. Some do, because they went through a circuitous route to a professorship, or just because between undergraduate and graduate school they went into industry, but oftentimes people don't know of another path besides one of those three: the teaching, the research, or a combination of both. I mean, what else can you do? And it's really unfortunate, because I think an increasing, I saw statistics just the other year about how an increasing number of, or percent even, of PhDs are not following any of those routes. They're going into programs like even Peace Corps, and then figuring things out from there. So a lot of them go into industry. A lot of them go into government administration kind of roles. Some of them go into policy. I think with climate, those are becoming more and more common from what I see. But so I also have a policy degree. I did that while I was in graduate school. I was too curious. I wasn't the ocean's role in climate research that I do wasn't close enough to humans, so I did that out of curiosity. It's everything I should have learned as an undergrad, I feel like. But it's a combination of political science, economics, and statistics. And the statistics is just the tool that you use to interpret the economics and political science. From talking to people who have asked me about that policy degree over the years, it doesn't seem like people know exactly what that means. People don't know the difference between law and policy. People aren't sure whether policy means you're writing legislation, or so. I mean, how are you supposed to get across all of these points when also So one of my other slides here, I don't know if we need to go to it, but is about how just a lot of the struggles people go through in graduate school, and how it's different from the paths that people take just going straight into industry. People will, a surprising number of people have some sort of mental illness, and by mental illness, it's nothing to be ashamed of, because you're going through a somewhat traumatic experience a lot of the time, especially if you're harassed or racially profiled on campus, or what, or just are now finally on your own, away from traumatic experiences in your childhood, or that you're financially struggling and you're living in the bottom of the basement of the library because you can't live on the income you stipend you get as a graduate student, and you need to support your family back home at the same time. There's a litany of issues.
Yep. Well, that's a similar thinking that, like you said, everyone kind of goes through that. I did that when I first got out of college. I actually had a minor in environmental science and policy. But I soon realized that you really couldn't go anywhere with just a bachelor's degree other than being, collecting samples and being a lab rat. That's pretty much what you were confined to. So I determined that I had to go into a graduate studies of some kind, and I realized either I could go into like teaching and be done in 2 years, or my other option was I was considering going into chemistry, getting a master's in chemistry, which would have taken me, at minimum 2, if not 3 or 4 years to go through an actual, master's thesis and through the program. And I was at that point, I wanted to get married. I wanted to start having a family, wanted to have, a decent job, because I had been working in a lab for a number of years, which kind of sucked. But, and so like you had to make that decision. Like you said, it can be stressful, because essentially at that time is when you're making that decision for, the rest of your life. And then of course I had professors that once you decide to go into education, they dismiss you completely. But,
yeah. So, I mean, so the unique challenge with graduate school, just what I was trying to say is, I mean, people, those experiences in people's lives, regardless of what profession they go into, you can have those. But then the unique feature here of being in graduate school and also having to deal with those issues is that you think that you go to graduate school with the impression that there might be a straightforward path for you if you make it as a researcher, but that's less and less the case now. I mean, there's all sorts of uncertainty thrown in here, and when you have many of those other issues, I mean, your anxiety is going to go through the roof. You're going to be indecisive. It's going to be extremely difficult for you to find what it takes to make it as a researcher and beyond your PhD. And I mean, I know that I struggled a lot with it. I certainly had a lot of anxiety through graduate school. And I'm still here today doing research in the field, so I don't want to scare anyone off and say that it's that's a recipe for disaster or anything. It's one of your students.
Yep. Yep, Vinny's here.
So it's just the crossroads of all those different factors is pretty unique when it comes to doing a PhD. It's risky but also rewarding. I would say I should say something positive about it. It's pretty rewarding sometimes when you find out something cool.
You're probably reading that as well.
Yeah.
Yep. I agree with Bulber. That's an undergrad as well, I think. It's not what you know, it's who you know. That whole thing. I think that's where getting to know your professors well and going to presentations and conferences with people allows those connections. I never valued them as much as I did when I started teaching. But David, do you want to talk about that as well?
Yeah, so if you have an advisor that doesn't have the funds to it doesn't have the funds to send you to a conference, for example, that's bad.
Right.
You're not going to make a lot of connections that way. And also, I mean, graduate students of this time, during the pandemic, you should be attending a virtual conference at the very least, because but I don't know how you're going to network the same way, because these breakout rooms that people have at these virtual meetings, it just isn't the same as meeting with people, stumbling across people and going up to them, talking about their research after they give a talk, or just sending them a message afterwards and saying you want to meet them because you want to talk about a research idea, or that you have an idea and you message them.
Yeah.
Yeah. So. And there's basically no information about things other than the classic route, but there are starting to be some fellowships, at least if you search for them online. If you know to search for them, there are some fellowships that can try to bridge the business world with academia in order to do unique research there. But when you're thinking about going to graduate school, I feel like at least I was going in completely blind. I had no idea all these possibilities existed. What funding was possible. It constrains a lot of what you can do, because I mean, unless you have unlimited financial resources, I would say that it constrains whatever.
Yeah, I will add, I was on social media the last few days looking at some of the PhD chats and a lot of graduate students, because I was looking for people I might want to have on as guests, and there's a lot of stress. People had just finished up, defending, or they finally have their first break and they feel guilty because they're not devoting every minute to what it was they were doing. And so they have some time off. They don't even know what to do with it, really. I find that that's really, interesting. And I think there's also, and this is common in every field, is that imposter syndrome. And you alluded to this, where you always don't feel like you belong in a way, and you're kind of making it up as you go. And I think a lot of people feel that way, especially when they first start getting into a field. And there's so many other really, big stars and people doing great research. It's kind of overwhelming.
Yeah. Yeah. So in oceanography, it's a small enough field that you can get a grasp in your head of just the names that you can rattle off the top of your head, that are the big name researchers for. That you should read the papers by, and then that you might want to meet or get to come by and see your poster or talk or whatever at a conference, and you should reach out to try to get those people to attend, if it's relevant to what they do. But yeah, I had a lot of anxiety as I was saying, and so I did not do that at first. And the way that I even got a postdoc was that okay. So there's a longer story here. My PhD advisor had the same PhD advisor, when she was doing her PhD, as my first postdoc advisor. That was the connection. And and he made the connection when he saw my CV. And that's the only reason why my CV popped out to him, I think, at the time. But the only reason why I was able to interview there, because he didn't have the money to fly anyone out. So the only reason why or maybe he did, but he didn't want to. But what I did was I found another place to interview at that did fly me out. This was just coincidental, actually. It wasn't purposeful, but I tried to make the timing of meeting with him coincide with the timing of when I was flown out for this other interview. So I got to meet him in person and present the work that I've done. When that other interview had me also give a presentation, but they couldn't give me a decision for many months. And my first postdoc advisor gave me an offer and said, you have to make a decision soon. And I'm risk averse, so and also he does research in oceanography, whereas this one that flew me out actually was this interdisciplinary thing where it was kind of policy related, climate science policy related, which would have been cool, but I couldn't risk it because I was pretty much bankrupt at the time. In fact, I was homeless for a little bit. But, I was treated accordingly in Seattle.
Well, I'm glad things turned out well for you. Seems like, at least got a roof over your head now. So
yeah. Paying an exorbitant amount of money for DC rent.
Yeah. That's why you got to move out to Baltimore, where it's a little bit cheaper.
Yep.
And the traffic in DC is terrible. But okay, well, this was a great conversation, David. It was great having you on. We've been chatting for almost 2 hours now, so I think that's.
Oh yeah.
Yeah, you're like, oh yeah. I think that's enough of our time.
Okay.
And thanks for stopping in and let us know about you and your research. And we'll be in touch. And please, if you know of anyone else within your circle, talk about networking, that wouldn't mind spending a little bit of time with me and the rest of Twitch, please let me know. I'd love to have them on to talk about pretty much any topic in science. But climate change seems to be really popular right now, as it should be. So thank you.
Great. I really appreciate having me on. And yeah, I'll let you know.
Awesome.
About other prospects, people to have on. I have some people in mind.
Awesome. Great. Well, I learned a lot tonight. And hopefully, anyone else that watches this, I'll have this up on YouTube in a little bit as well. So anyone else that wants to sit and listen to us talk for 2 hours can do so. But thank you so much for the conversation.
All right. Yeah. Thank you. Stay well.
Yep. Okay, everybody else, we are going to say good night and goodbye. All right. Bye.